For students on Zoom, can you hear me? For students on Zoom, can you hear me? Okay, great.
Yes.
Thank you. So let's get started. I was planning to talk about the heat transfer chapter in this class, like one chapter in one class, but then I figured out probably it's more helpful for you guys if I talk about project, like Q&A session. So I want to say that this semester goes a little bit slower than the previous semester when I taught the FEA web several years ago. Department stopped me teaching FEA for many years. So I will say that a little bit slow is not necessarily a bad thing. In previous semester when I taught FEA, I cover the heat transfer, but this semester, as you can see, that we really don't have enough time. I think well, hurricane is one thing, and the other thing is that this is the first time I teach this class in person after COVID. And previously, when I did it on Zoom, it's like everybody turn off the video and mute it, and there was no question asked during the class, and I could go very fast. I didn't know if students understand or not. So in previous semester, I covered a lot more materials, and this semester, I really enjoyed the interaction with all of you sitting in the classroom and with question, and I could explain things in a more clear way. And it's like really customize this class to your needs. And that's why this class this semester is a little bit slower. But I feel like seriously, this is not really a bad thing, because it's not about how much I can teach. Well, I can go very, very fast, cover a lot of materials in textbook, but if you guys don't understand, there's no point. So I think it's about how much you guys can understand. So I think it's okay for not covering the heat transfer chapter. And if you get a general idea of this semester, you know that, to be honest, each chapter is the same thing, right? We find the K matrix, we do the interpolation, we calculate nodal degree freedom. For the heat transfer problem, we just model it as a 1D problem and how the heat transfer will go. So it's the same thing. So if you're interested, you can read the textbook, and based on the thing that we already accumulated in this semester, I think it's pretty easy to understand. I think that chapter is actually easier than the plane stress part. So that's the new content of this semester. So for the project, I think it's better to do a Q&A session, because the tutorial video is not a good quality. I know that, but it's really hard to do the tutorial in this class because classroom, the half of the classroom cannot see if I use my laptop and the project here. So just for this project, specifically for this project, what question do you guys have? And I can answer you guys.
Should we do that using local steam edges and then just increase the number of elements where there's high stress, or should we just like go to partition and then just like make more like partitions where there's high stress and then use like a global instance for the steam?
For convergence study, right? So for convergence study, I would suggest just use the global side for the whole part, because it's really hard to control that you use small, well, after graduate, when you go to industry, you probably will do like, okay, I only focus on a small area, and for the rest part, we really don't care. So we just use large element. That's the most efficient way. But for our talk harm, is a much simpler situation, and to make it like easy to compare, I think it just like is the global Cs for the whole structure. There's no need like you find the high stress area and put more C there, because in that way, for different number of elements, you really hard to control, like, okay, increase double the element size or double the number of nodes, and then you really don't know which area you want to put like more elements which area use larger elements. So for our convergence study to have a nice convergence rate, and for our simple, relatively simple application, you just use the same size for the whole structure. Yeah, you still do partition. So partition is still the same, but when you do the seeding and you choose a size, you use the same size for the whole structure. You do not need to like, okay, I figure out this area is like a much higher stress, so we focus on this area, and which you use much smaller size this area, because in that way, it's not easy to get a good convergence rate. Yeah. So I guess because it's like too far away, I guess the question is about the partition, right? Yeah. So partition, the basic, there's no standard solution partition. We just want to make the region, let's say, in our FEA class, we talk about that. Okay, sorry. The reference. This is always reference element, S and T. And the most accurate result is when our actual element, the shape is getting closer to this reference element. So the mapping is more accurate. And the more your element is distorted, let's say if you have a element like this, the angle is more distorted, the more inaccurate result you will have. So what we want to see is that after partition, your area has like 4 edges and all the edges getting closer to 90 degrees. If not, I think the abacus constraint it to 15 to 165. So if it's beyond this, like if the angle is smaller than 15 or greater than 165, you can see that in abacus it will just show a purple area and see, okay, this area is not properly partitioned. So you need to do it again. So I would say that, again, there's no standard solution, but something you can try is that, okay, let's say we do something here. Then we can see, or maybe this one is not necessary. So in this area, I think it should be fine. As this is one edge, this is one edge, and these 2 edges. And you can see that this, you can try things abacus. If you partition this one as one region, you should be fine. And for this side, I can do something symmetric because structure is symmetric. And maybe something like this. And now you can see that this area becomes one region, and this one region, and this one region. But there's no guarantee that this is the best way. So you just keep trying until the abacus allow you to keep continue with the mesh. So so the general rule is that we want to make sure that the angle is not too much distorted, like deviated from 90 degrees, because it's just deviated from 90 degrees, the more inaccurate result we have. So that's the rule. No, so you can try. So you can use a free mesh. So you do not need to do any partition, and you will see that the mesh is really a mess. So I think in my 5th tutorial, I show this structure, and I use free mesh. the mesh quantity is really not good. So I think it's better that you do the partition and you have better results. And when you do the convergence study, you will have better convergence rate and have a nice plot. And also it's not just like I want to torture you guys to do the mesh and everything. It's something I want you guys to learn, because if you know how to do the partition, you know how to control the seed and how to mesh the structure in the way you want. And for this one, probably it's fine because this structure is simple enough. But when you go to industry, you have a huge structure or much more complicated structure. You really want to have some control how you want to do the mesh. It's not like same element size everywhere. As just he said, we may need to focus on small area. Like when I see this structure, I know, okay, there must be somewhere in this region may have higher stress in the rest of the region. So in the higher stress region, I can have smaller element size. And for the rest of the region, it's fine, it's safe. So I use larger element size. So we can save some computation time. And the partition is a way that we can control this mesh. So in one region, we use small element size. The rest of the region, we use larger element size. So it's indeed something I want you guys to learn. So try to do the partition first. And in the previous years, some students like keep trying for several hours. Still, there's always some purple areas. It doesn't work. I really don't want to know because when I tried myself, it works fine. But in case that happened, I really don't want you guys to see you guys have depression at the end of the semester. There's one way that you can do. So this way, it is free mesh. You don't need to do the partition. You use media axis. So this one can give a relatively better mesh quality than just use free mesh alone. So this one is not included in my tutorial video because this is something new in Abacus in recent years. My Abacus tutorial was when I was second year in my PhD. So that was like several years ago. So this is something new in the Abacus. It is much easier than because if you use this one, you really don't need partition, but still try to do partition first. It's something I really want you guys to learn. And if somehow you are really tortured by the partition thing, I'm okay with this one. So this is what I want to say. I don't want you guys to spend unlimited amount of time on one project just in my class for my class. So I know you guys are crazy busy at this time. So this is just like something like backup plan. Any other question? Have you learned stress concentration in mechanics materials? Have you learned that larger radius has less stress concentration effect and smaller radius has higher stress concentration effect? Right. So I guess when you try in Abacus, it shows somewhere here. Is that correct? Why is that? Well, based on our understanding of mechanics material, we simplify this as a kind of a beam. We clamp here, and we have force applied like this, and there's a bending. It will bend in this way, and we expect, okay, this is a maximum bending moment, and the stress concentration, well, is either at top and at bottom. And of course, because we have compression, so probably high stress is top because compression plus compression, right? This one is tension plus compression. Anybody confused or you guys okay? So based on understanding of mechanics materials, it should be somewhere here. That's what you just talked about. But consider the stress concentration. This area, this radius here of this circle is much larger than this one. And the stress concentration, when it's high enough, it can raise 3 times of the nominal stress. So it does contribute a lot. So that's why when you put everything in abacus, the high stress is not here, but somewhere here. Stress concentration. Any other question? Yes. So let's say, I think the project intentionally require you guys to know how to use the units. So if you use the centimeter or the length unit, in the result should be centimeter. And if you have the Newton and everything, it should be Newton, centimeter, everything. So you need to know how to convert. And make sure that this is clear at the very beginning, because I knew that from my previous semester, some students like, in the end, they have really weird results, and they have the report like almost done, and they told me why the result is weird, and check for a long time and figure out, okay, you did it wrong, and then they feel like I don't want to correct that, so because just take too much of it. You need to correct from the very beginning. So make sure that units is correct at the very beginning, so you do not need to redo the whole thing.
So if we use instead of millimeters, we like convert it.
Use centimeter. You are required to use centimeter.
Oh, instead of, okay. So if you got results that were correct, but in a different unit, like multiplied by 10 or 100 or something like that, and we stated that, would that be acceptable?
We want to test you the unit conversion and everything, and consistent in abacus by using centimeter. So you just use centimeter. There's no other option. Yeah, it's not like what is the best convenient way for you to do. It's like we want to know if you know how to convert and how to make it consistent in the whole project. Any other question? Use centimeter.
Would that be like vertically aligned with the whole application point, or would it be like anywhere on the circumference of the whole?
So, good question. For the displacement at node at this node, well, actually, when you do the sketch, there's no point here, right? This is just empty hole. But remember that when you do the MPC constraint, you create a reference point here. Right. So actually in abacus, they allow you to find the displacement at this point. So when you do the check the result in abacus, you can use tools query, and then they will show displacement, and you just click on this node, it will show the displacement at this node in X direction, Y direction, and Z direction. And of course in Z direction 0, because this is plane stress. But abacus, as long as you have created a reference point at here, abacus, you use tool inquiry and displacement, and you click at this node, it will show the displacement result.
And then for the first half of the I guess when we're trying to find like the displacement, I guess it would just be like along that section, like along I guess the vertically line part like next 42 centimeters.
So let's see. I think there's some question also. Oh no. Let's talk about the preliminary analysis, because I think some students are very confused about this, so I can spend more time talk about in detail, and then you can ask me your question. Is that okay? So for the preliminary analysis, we want to use mechanics materials to calculate what is the bounding stress, what is displacement. And based on the question asked before the holiday and also in the during the office hour, I think some students are confused, like the preliminary analysis should be the accurate result, and how to simplify the model, how to simplify this model to have accurate result. So maybe this is like confused because of my tutorial 4 video I watched this morning. The tutorial 4 video, because in that video we did preliminary analysis, but that video we use a model like this. For this problem, yes, we have accurate result. We use mechanics materials, this pure bending problem. We can find maximum stress, exact maximum stress, exact displacement at the tip using mechanics materials, because this one is simple enough. But for our problem, for this structure, there's no accurate result that you can calculate from mechanics materials. So it's just different students can have your own understanding and your own way to have the preliminary analysis, and all of them, they just give us an approximation. And it really doesn't matter like who is more accurate, it really doesn't matter, because in the end, we just want to make sure that the result from abacus is not weird. Because in the previous semester, some students like did something wrong, like boundary condition, loading condition, mesh, or anything, define something wrong. They have like several order magnitude off results. So our preliminary analysis is just want to make sure that, okay, the result it calculates from hand calculation and the result from the abacus, they are in the same order magnitude. So to make sure that there's no weird mistake in abacus simulation. So for this, simplify this model and we use mechanics materials, we know that, well, mechanics materials, we never learned how to calculate the beam with the cutout in the middle, right? We didn't, right? So the only thing we could do is that, again, left side, boundary condition, since it's fixed here, right? Fixed at this point. So we can consider, well, it's clamped. And the length of the beam, since we are applying the force here, so we can consider this is the length of the beam. So this part is easy. The part that you need to make a decision is the height of the beam. The thickness is simple. The thickness is same as our thickness, right? The height. So how do we define the height of the beam? I would say that, okay, it's probably, let's consider this is the middle point. Well, it doesn't have, like, doesn't need to be exact middle point. So as you can see that if there's no cutout in the middle, probably this one is, I think it's a reasonable approximation, right? It's like, let's assume that this is the middle point of this line. So I think it's reasonable. And because of this cutout, it actually make our beam less rigid. So we can consider maybe a little bit smaller because there's a cutout. But how much smaller? It just make a decision yourself. There's really no standard way. So I would say that if consider without the cutout and the middle point, we consider is H1. And if the cutout, let's make this one clear. So let's say that this is H1. And this is the cutout is H2. So H1 minus H2 should be somewhere in between, right? And for like which value you want to choose, you can just choose. Just make sure that it is a reasonable value, and there's really nothing like standard solution for this one, and anybody can get an accurate result by this hand calculation. No, and we cannot say that hand calculation is more accurate than abacus or abacus is more accurate, because both abacus and hand calculation are approximation. So if you want to get a better result, you do convergence study, and you will see how it converge gradually to the accurate results. And for this preliminary analysis, again, we have the length, we have the height, and we have the thickness, right? We can do the calculation. And be careful, the question asks about the von Mises stress. Calculate maximum von Mises stress. So let's say if we just simplify it as a bin. Let's say we already have all the dimensions, and we have force, where is the location to have maximum von Mises stress? Where? For this kind of a being, it should be here, right? Why is this place? Yes, yes. So let's say, thank you. So for purely this force, it will generate a bending. And the bending will bend in this way. So we know that it has maximum tensile stress here and maximum compressive stress here, right? This is for the vertical force. And for this horizontal force, well, compressive stress constant through the whole cross section. So we know that maximum bending moment is definitely at the boundary condition, but we know that at the bottom surface is tensile from the bending and compressive stress from the compression from this horizontal force, right? But on the top surface, we have compressive from bending and compressive from this one. So compressive plus compressive is higher. But this only explains the sigma xx, right? The question asked about the von Mises stress. Does this change our critical location if I ask you about the maximum von Mises stress instead of sigma xx? So we know that, again, mechanics materials, we know that for this force, it's not just bending, right? It also has transverse shear. So this one, transverse shear, it will generate shear stress here. Well, the whole cross section, of course, but the whole beam. But this is we know that this is a critical location. So we know that there is shear stress generated by this vertical force. But does it change our conclusion if my question is not maximum normal stress, but maximum von Mises stress? No? Why? Transverse shear stress. Ready? Ready? Anybody has other opinion? I'm sorry. So raise your hand if you think that shear stress is constant across the over the cross section. Raise your hand if you think it changed and how it changed. Anybody answer me? How does shear stress should change? Yes. How does it increase? Like linear increase or quadratic increase or cubic? Thank you. Thank you. Yes, it's quadratic change. So back to the mechanics materials. If you have a force, transverse force here, it will generate shear stress. And at the cross section, the magnitude of shear stress should quadratic change. It is 0 at top and bottom, and it's maximum at the neutral surface. And it's quadratic change, so you can consider in terms of magnitude, I can put it in this way. And for the direction, of course, upward. And if we know that, okay, it will just this vertical force will generate shear stress, but at this location, it really doesn't matter, right? Because at this top point, shear stress is 0. So if shear stress is 0, von Mises stress is equal to sigma xx. Am I right? So again, this will require you guys like solid understanding in mechanics materials. And I think this is very important. The question did indeed ask you about the von Mises stress, but because we already identified this is a critical location. Well, some people may say, okay, what if the shear stress is larger than sigma xx? If you did a lot of calculation in mechanics materials, we know that for the same force, when it generates normal stress by bending and the shear stress caused by the transverse shear force, the bending, normal stress caused by bending always dominate, right? It's much larger than the shear stress caused by transverse shear. So we know that the shear stress, no matter what, even at the neutral surface, it should be much smaller than the normal stress in terms of magnitude. So we know that there's no problem. This is the critical location. And if this is a critical location, and for shear stress, it is 0 here. So we know that von Mises stress is equal to sigma xx. Yeah, so good question. So let's only focus on this point. If let's say in the mechanics material, we talk about like small element and we have like normal stress, shear stress, normal stress in different direction, shear stress in different direction, and we calculate principal stress is like what you just said, right? And that's like stress transformation and everything. So if the element, let's say this element I took from this point, it only has normal stress, it means that this normal stress is the maximum principal stress. And the other principal stress is 0. So, well, you can do the detailed calculation like, okay, for our state stress at that point, at the critical point, we have the sigma xx and what if you want to use the standard procedure, what is the principal stress and what is the von Mises stress, in the end, you will get a conclusion that von Mises stress is equal to sigma xx because there's only one normal stress. Any other question? Did the problem statement say how many iterations? Change 3 design to reduce the mass as much as possible while it has maximum von Mises stress less than. Okay, it doesn't specifically say that how many iterations. I would say same as project 1, 4 or 5 iterations. I definitely don't want you guys to like spend an unlimited amount of time to do the iteration by hand calculation. Well, we need to make sure that maximum von Mises stress below the less than the maximum normal stress, that's for sure. But for the like reduce the mass as much as possible, this one, just do 4 iteration or 5 iteration and it should be fine. Yeah. Any other question? ODB file is output database. So this one, right? You can so you go back to the file. So the file, the same folder that you check the like input file, RPT file, and everything, you should have something like something.odb. Yeah, just submit that one. Any other question? Also, I want to talk about the for the constraint geometry. So this one, I'm not sure if you guys tried or not. So my tutorial, I think what I did is I didn't make it for the constraint because in that example I did in class, there's no change of design. So there's really not necessary to do the 40 constraint. You just put it there, and the line, they are yellow, they're not green. Green is 40 constraint, and yellow means it's not constrained. So basically what you need to do is that how to make this line become green and 40 constraint. Let's say if you make this one, this center of the circle as a fixed point, let's say you make this center circle at 0, 0 or any fixed point. So you make this point fixed. And then you define the radius of the circle. This circle will turn green. If you don't define this center point or radius, either one of them, and just draw a circle, the circle should be yellow. Anybody try this one on Abacus? Have you guys successfully make it green? And also, let's say, I think in this one, what I did is to make the construction line. So this is one construction line, horizontal line. This is a vertical construction line, and you can define the coordinate of this point, and then you make this one it's a fixed point, and also this is the same point of the central circle. And once this point, the central circle is fixed, the radius is fixed, this circle becomes 40 constraint, right? And it will turn green. And the same thing here. So for this one, you can make the central circle, of course, there's a distance. You know the relative distance. You can, if you define this central circle, it's on this horizontal line, and you define this distance, it means that the central circle is fixed, and the radius, you define the radius, and this circle will turn green. And the same thing, there's a tangent relation here, tangent relation. So in the constraint, in the sketch, in the constraint, you can just put the tangent there. And in this way, so when we change the design, so the parameter we need to change is x1, x2, x3. So when we change the design, it will make sure that, let's say, if you define this circle, well, it's a half circle, but when you do the sketch, it should be a whole circle, and there's a center of a circle here. The x1, what is x1? Wait a second. x1, x2, okay, here. It will make sure that central circle, it will move on this horizontal construction line, and the change x1 will only move this point center circle, which means this point left and right. It will not move this point because this point you already fixed. So this can change the design the way you want. And also x2 is this radius. So when you fix the central circle on this horizontal construction line, the central circle will not move up and down. So when you change the radius, and the same thing, x3 is this distance. So this is how to make it your geometry 40 constraint, make all the line green. You may need to try several times because, and a lot of times, so let's say when you do the sketch, you need to draw a full circle first, and then you use a tangent relation of the straight line and a circle and everything. And then you need to trim part of the circle, right? And after you trim, you can see that the part become yellow again, because that's because they define that if you trim half the circle, they lost the definition of the radial circle. So you need to redefine the radius and it will turn green. So you need to just keep trying until everything turns green. So once you make it fully constrained, then when you change the design, it will change in the way you want. Otherwise, the like center circle will just jump everywhere. So let me check anything else. And for this 4-node triangle, 4-node quadrilateral, 6-node triangle, 8-node quadrilateral. So basically, this is controlled by when you do the mesh. So in the mesh, they allow you to choose. I think it's element control. You can choose the linear element and quadratic element, right? And also in the element type, you can choose triangular element and rectangular element or quadrilateral element, sorry. Quadratic, sorry. So in the element control, you can choose linear element or quadratic element, and element type, you can choose triangle element or quadrilateral element. And there's also one option that is the quad dominate, don't use this one. So this one basically for complicated geometry, they will use majority part use the quadrilateral element, and for the rest small part they use triangle element. But when we really want to do some comparison or convergence study, it's better just use either quad or tri. So tri means triangle, quad means quadrilateral. So if you can control this for the order of the element type and the shape of the element, then you can see that if it's linear and this triangle element, it should become the 3-node triangle. So it's CST. If it's quadratic, then this is LST. And if it's rectangular, and this should be the Q4. And this should be Q8. So this is how you change the element, different element by control the mesh. Any other question? Let me see if there's any. Write down your name and UFID on one paper and submit. And we have office hour every day. So I have office hour Monday, Wednesday, Friday. TA have office hour Tuesday, Thursday. So if you have any question related to this project, come to our office hour. It's much, much easier for us, not just for me and TA. It's also easier for you to solve the problem through by coming to our office hour. Email is really hard to explain. It's like we email back and forth for 1 hour. Sometimes we can just talk face to face in 5 minutes. So try to come to our office hour for any question. Thank you. Thank you.
Still having our exam 3 on Friday?
Yes. Wednesday will be the exam review.
Thank you.
You're welcome. Good question. I need to ask TA.
There's class Wednesday, right?
Yes. Okay. Exam review.
Oh, yeah, I had a question. Is exam 3 still on Friday?
Yes.
Okay.
Yes.
Do you know when our first project?
One student just asked me that question.
okay.
I need to ask TA.
Hours during exam week.
Exam week? Yeah, it's like the 7th to the 12th, I think, something, whatever. Yeah,
The project's gonna do.
yeah,
Okay.
yeah. I will have office hours before until the project.
Okay.
Yeah.
So
But start early. Don't wait until last minute.
it's the exam.
Okay.
Full attention.
Okay, sure.
Is the exam still Friday?
Yes, Friday.
So do we have class?
Exam review.
And then, but we don't have class.
No, no.
Oh, but we have class next week. Like the Monday and Wednesday.
No, what do you want to have class after exam?
Okay, so after the exam.
No, there's no class after exam.
This is the elastic modulus. We would have to change the units of that, right? And I kind of realized I did it in newtons per meter squared, and my deflections were very small. So I'm kind of realizing, do you think that could be it?
How much you have done on your project?
A lot.
A lot.
I can go through and read it. Like I didn't do step 5, and then just 3 and 4 should be easy to change, I guess.
We still have enough time.
Yeah, I was doing it
Because I really don't know like how much penalty you have.
No, yeah, I'll redo it.
Yeah.
It's just
So
I'll redo it.
So
later.
since you know how to do it, so redo it is pretty fast.
Yeah, I thought
Yeah.
to save it for later.
Yeah.
Because I have
Yeah.
other projects.
Sure.
you.
Sure.
Even for like the 6-node triangle and the 8-node like quadrilateral, are those even like approximate to? It's like the is the quadratic still not enough for the exact solution?
Quadratic give you better results,
Okay.
but there's no element type can give you accurate result because based on our geometry, it's just too complicated to have accurate result. The only approximated accurate result, I would say, is by convergence study. You plot, and in convergence study, you have the U naught. That is the approximation of exact.
Okay, that
Yeah.
makes sense. Thank you.
Yeah.
Thank you.
Welcome. Hi.
Hey, so I'm kind of confused about how you figure out the edge length. Like for
Edge length.
for square, I totally understand. Like you divide it, or you take the square root of the.
Homework.
Yeah,
Okay, I thought it's project.
it's like you put that over the number of elements, right?
Let
But like,
me check. The homework 10, right?
Yep.
Homework 10. This one?
Mhm.
So a mesh with 64 and a mesh of 16. So similar as in the example in class,
Mhm.
that one we assumed is constant A, constant area.
Mhm.
And this one we assumed constant volume
Constant volume.
because, well, volume is the same,
Oh, okay.
right?
Yeah.
And then we assume that it's constant volume V divided by, it says the whole structure, the volume is V. And if it's 1600,
Oh, you take the cube root.
yeah.
Okay,
So this is actually,
that makes more sense.
Yeah.
So you do constant volume because it's 3D instead of 2D, right?
correct.
Okay, that makes sense.
Because no matter how we mesh, the whole structure, the volume is the same for
Uh-huh.
3D situation. And for 2D, the whole area is the same.
Mhm.
So we just assume that this is V and total number of elements, and this is the edge length.
Gotcha. So for 2D, what if it was a triangle? Would you still do A or would it be 2A since its area of a triangle is 1/2?
Well, in the end, you just need a ratio.
Oh yeah, true. I guess it
So it doesn't matter.
It
So you just
cancels.
use A. Yeah,
Okay.
yeah. It's in the end, it's a ratio.
Mhm.
Yeah.
Okay, cool. That makes sense. Thank you.
Yeah, no problem. Hi.
What do you question about homework?
Okay.
need to calculate the strain at this point.
Yeah.
And the displacement of node 1 is positive.
Mm.
So then the strain should be positive too, right? Because my result is negative, but
Wait. What is it positive? What?
my
was-
strain result
Okay.
is like a negative strain, but I would think it expands.
U1 V1 is point. So U1 V1. So it goes in this way.
Yeah.
Character string. It should be positive.
Yeah. And that's what I'm confused. I've made some mistake, but
Let me confirm. Let me confirm. Yes, it's possible. Check your calculation. This
Yeah.
same procedure as example in class. So method should be fine. Just
Okay.
calculation problem.
Yeah.
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 I had algebra issues in my exam. I missed 16 points.
Oh,
What?
Yeah, they took four because it was minors, then that's all. So is that the answer? Can you like say, or you're not allowed to do that?
Let me check.
First question.
Okay, correct.
But don't share this information in
No.
group chat or
Of course,
anything.
no. So in my last question, I don't think my procedure is correct, but that's what I did. So I just took the ratios that I found you not.
No. Because this 1600 and 6400, you cannot just use derivative. That is not the element size. That's not H definition. H is element size.
Oh, so but the method is correct. I just need to find the correct.
H.
Okay.
So remember, I emphasized in class that the H, the 1600 and 6400, they are number
They're
variable,
not well.
and H is the H length of each element. So you really need to figure out what is the H.
But if I figure the age, the procedure is correct. Thank you.
You're welcome.